Okay, now we are going to have a look at few point processing operations. Okay, so basically we can use various point processing operations to enhance the image, given image by some means. Okay, so there are various point processing operations like contrast stretching, piecewise linear transformations, bit plane slicing, logarithmic transformations, image negative, power law transformations. Okay, so there are many image enhancement operations which are under domain of point processing operations. Okay, so we are going to have a look at few of these point processing operations. So before starting with actual operations, let us understand what do you mean by point processing. Okay, so basically this point processing is a simplest kind of image enhancement operation. Now meaning of point processing is to process the image point by point. Now what is the smallest point in an image? It is pixel. Okay, so when we apply some function on each and every pixel of the image, it is nothing but point processing. Okay, so we apply a function t on original pixel value r to determine enhanced pixel value s, enhanced pixel value or processed pixel value. So r is your original pixel value. R is given by, r is function of xy, means here x and y represent x and y coordinates of the image, and f of xy is nothing but intensity value or gray value of the pixel at location xy. Okay, so r is pixel value at location xy in the given image. On this pixel value r, we apply a function t to get enhanced pixel value s. So this is nothing but point processing. We simply apply a function on original gray value to get modified gray value or enhanced gray value. Okay, this is meaning of point processing. Now let us see how this point processing is useful in image processing. So one of the important operation, point processing operation, is contrast stretching. So many times, though we have a camera with very good dynamic range, your captured image has low contrast. It is mainly because of poor illumination conditions. So if you capture an image in dark, you get dark image which has very, very low contrast. Similarly, if your object is over illuminated, in that case also captured image has low contrast. Okay, so to improve the contrast or to stretch the contrast, we can use one of the point processing technique, and the technique is named as contrast stretching. So it basically improves the contrast in an image by stretching the range of intensity values to span a desired range of values. So let us understand this statement. So as shown here in this curve, this x-axis represents your original gray value. Okay, R is the notation that we are using throughout this lecture for original gray value, and S is the notation that we are using for enhanced gray value or modified gray value. So here x-axis represents original gray value and y-axis represents T of R, that is modified gray value. And this graph gives you relation between R and S. Okay, so mapping between R and S is indicated by this particular curve. Okay, now for contrast stretching, we use this S-shaped curve. Now, if you look at this curve, just focus on the central portion. So what we are doing at this central region, basically this smaller gray range, original gray range, we are stretching it over greater range. If you look at the x-axis and y-axis, this small gray range, say between R1 and R2, it is spread over greater range on this s-axis. Okay, so as if we are stretching the gray values, we are stretching the original narrow gray range over wide gray range. Okay, and whenever we are stretching the range, resultant image has better contrast, because now the resultant image has greater dynamic range. By this stretching operation, we are increasing the difference between darkest spot and brightest spot, and that it means you are increasing the contrast. Okay, so this simple stretching operation, this simple point processing operation can give you better contrast. Okay, so basically this is S-shaped curve. With S-shaped curve, we can stretch particular range. Okay. And if you look at this lower portion, at lower portion, what is happening? We are making dark pixels more darker. And if you look at this upper portion, what we are achieving here, we are making bright pixels more brighter. So effectively, this S-shaped curve is very useful to improve contrast of the image. Okay. Now let us see how we can practically achieve this contrast stretching operation. So we can achieve it by piecewise linearization. Okay. So as discussed, basically this central portion, this linear part contributes to the contrast stretching. Now this S-shaped curve we can approximate by piecewise linear operation. This central portion we can approximate it by straight line or line segment. Similarly, this upper portion we can approximate by another segment, and this lower portion we can approximate by third line segment. Okay, so we can use piecewise linearization for implementation of this S-shaped curve. Because if we try to implement S-shaped curve as it is, we need greater number of computations and greater amount of storage. So instead of that, to make this practical implementation simpler, we can approximate it by piecewise linear segments. This entire S-shaped curve we can approximate by 3 line segments. This is your first line segment. This one is middle portion is your second line segment, and this is your third line segment. So when we approximate it by 3 line segments, implementation becomes simpler. How it becomes simpler? Because in order to determine relation between R and S, we can simply use 3 equations of lines. One equation for this segment 1, second equation for segment 2, and third equation of line for line segment 3. Okay, and simply by using these equations of line for given value of R, we can determine new value of S. So thus this piecewise linear segmentation makes your practical implementation easy. So that's why we use this piecewise linear approximation. Okay, so this original S-shaped curve, which is continuous in nature, it will look like as shown here after piecewise linear transformation. Okay, so this is your contrast stretching operation in terms of piecewise linear transformation. So as we are using piecewise linear approximation, this is this contrast stretching is an example of piecewise linear transformation. Okay. Now, if you look at this curve, there are three line segments. This is your first segment, first line segment. This is second line segment, and this is third line segment. Okay. So if you look at this lower portion, 0 to R1, here, this 0 to R1 is mapped to 0 to S1, right? So 0 to R1 is much greater than 0 to S1. So because of this line segment 1, what we are doing is we are making original dark pixels darker than the original, because say almost 0 to L by 4, we are mapping it to 0 to L by 2. Okay, so your greater range, dark range 0 to R1, it is mapped only to 0 to L by 2. So we are making dark pixels more darker. So this is function of this line segment 1. Now by using this line segment 3, just look at the last portion. Here, your original bright gray shades, which are ranging between R2 to L minus 1, we are mapping them to S2 to L minus 1. So again, as compared to this range, R2 to L minus 1, this S2 to L minus 1 is much smaller. And all these are bright ranges. So original bright values, we are making them more bright. We are making them brighter than the original. So this is job of this line segment 3. And now look at the central portion, middle portion. So your central portion on x-axis, it varies from R1 to R2. Okay. And after mapping, we are this R1 becomes equivalent to S1 and R2 becomes equivalent to S2. So after mapping, your original narrow gray range, which was between R1 to R2, now it is mapped between S1 to S2, and this is much wider than the original shape. So this middle line segment, that is line segment 2, it is actually stretching your contrast, because it is converting narrow gray range to wider gray range between S1 and S2. So simply by this piecewise linear approximation, we are getting contrast stretching or contrast improvement. And because of this piecewise linearization, practical implementation becomes easy. Here we have three lines. Your first line is passing between 0, 0 and R1, S1. Second line is equation of line, which is passing through R1, S1 and R2, S2. And third line, you can represent by a line which is passing between 2 points R2, S2 and L minus 1, L minus 1. That is maximum intensity point. Okay. So simply by using these three equations of lines, we can convert original gray value R to new gray value S. So if your original gray value R is say L by 4, if it is L by 4, that is if the original gray value is less than R1, we can use this first line segment or equation of line for this segment to determine new gray value. Okay. Similarly, if your original gray value is between R1 and R2, we can use this second line to determine new gray values, which are of course between S1 and S2. Okay. So this is simple piecewise linear transformation to achieve contrast stretching. Okay. So this is original image when we apply this contrast stretching curve as shown here, when we apply it on this image, how we are applying it? We are applying it pixel by pixel. We take we read very first value of the pixel, that is R. We check whether this pixel value is less than R1 or between R1 and R2, or it is greater than R2. Accordingly, we use particular equation of line, either line segment 1, 2, or 3, and we determine new value of pixel. Okay. Then we go for next pixel and so on. So we can raster scan this image, and for each and every pixel value, we apply this transformation. And because of this transformation, we are getting this new image, which is representing all S values or modified values. And if you look at the result, you can say that contrast is improved as compared to original image. Okay. So that's all about today's lecture.